Hello everyone, welcome to our tutorial Contactless Health Monitoring with AI. I'm Wenjin Wang, currently the scientist of Philips Research and assistant professor of Eindhoven University of Technology. So today my part will be focused on the camera-based health monitoring. The camera can be used as a sensor to measure vital signs and body signs from human subjects, such as heart rate, respiration rate, SpO2, emotions, activities. This information can be related to the health state of a person. And this camera technology has been used in various applications, such as in the hospital care units, home-based monitoring, elderly care, baby care, fitness, automotive, for health monitoring. And especially now due to the outbreak of the coronavirus, contactless health monitoring is even more desired. Here is the 1-hour schedule of my presentation. I will first introduce two fundamental measurements, the pulse rate monitoring and respiration rate monitoring. And then I will show some applications from our group and finish the talk with the Q&A. So the first part is the camera-based pulse monitoring. Here is the introduction of the development from the contact PPG to the camera PPG. So the PPG is the abbreviation of the photoplethysmography, which is an optical measurement of the blood volume changes beneath the skin. You can see there are three different modes here. The first mode is the contact transmission measurement, where the light source and the photodetector are placed on two sides of the skin to measure the transmitted light through the skin. An example is the finger oximeter. And the second is the skin reflection measurement, which measures the light reflected from the skin, and the light source and photodetector are placed on the same side of the piece of the skin. An example is the smartwatch or wristband. And the third mode is the contactless reflection measurement, which will allow some distance or space between the setup and the skin. They replace the photodetector by a 2D camera. And this is called the camera PPG. So there's still some fundamental difference between the contact PPG and the camera PPG. So for the contact PPG, we can put the optical sensor and the light source in a specific skin sites such that it can construct a banana-shaped optical path that guarantee that the photodetector can sense the light that from the deep skin layers that contain the arterial blood position. But for the camera PPG, it sends the light reflected from the different skin layers, like the superficial skin layers that contain little blood pulse information. And also it may sense the mirror-like specular reflections directly from the skin surface that has no positive information. So the camera PPG signal is much weaker than the contact PPG signal, and thus more difficult to be extracted. But the benefit of the camera PPG is that the blood perfusion can be measured without perturbation. So it does not have the pressure from the contact sensors like in the contact PPG setup. And also there's a theory in our domain say that the camera PPG is not only measuring the arterial position, it may also measure the blood volume changes in the capillary bed. The reason is that when the blood volume is changing here, it will compress the capillary bed and change the blood volume there. So before going to the camera PPG, I would like to first mention two fundamental challenges for this measurement. The first is the skin melanin, because the melanin content will absorb a portion of the light and reduce the diffuse reflections, and especially for the darker skin that has the higher melanin content that will absorb more light and make the PPG extraction more difficult. And from this melanin absorption spectrum, what we can see is that it has higher absorption in the visible range than the near infrared range, which means that in the visible light, for example, the RGB camera is more sensitive to the melanin content. And for our experiment, we somehow show that for example, three different skin types, three subjects, And you can see that for the darker skin subject, especially the blue channel is heavily distorted, because for the blue, it is more sensitive to the melanin content. While the same three subjects in the near infrared, their signals are less different. And the second fundamental challenge is the makeup, because the makeup is similar to a neutral density filter that reduces the amount of light that can be penetrated into the skin. And this is the same for all the wavelengths. And then we conducted a study by putting the makeup on the forehead and measure the PPG signals in both the RGB case and also the near infrared case. And here is an example that for the for these subjects, if we put the makeup on the forehead, you can see that without makeup, the green channel shows a strong PPG signal. After putting the makeup here, the less pixels available, this is the PPG strength map, and the signal is much worse. And this is the same for the near infrared range. By putting the makeup on the forehead, we can hardly get any signal. And here's the overview of a basic camera PPG monitoring setup. It has three components: the light source, the skin, and the camera. The light penetrates into the skin, see the blood volume changes, reflect the back, and received by the camera. And our goal is to extract the PPG signal from the camera signal. And this is the basic workflow for the camera PPG extraction. The input are the video frames that include a subject. The first step would be the skin detection to detect the face, for example. And then from the skin, we measure the color signals, like RGB signals in the time domain. And then we extract one-dimensional pulse signal from the input color signals. So this process can be described in two sections. The section one is the PPG extraction, our core algorithms that how to measure the one-dimensional pulse signal from the multi-dimensional color signals. The second section is the PPG optimization, where we use different front ends to improve the robustness of this measurement. So I will start with the PPG extraction, our core algorithms. And here's the problem definition. Given a video with a subject, the subject may have some body motions, and from the subject skin pixels, like the forehead area, we can measure the color signals in the time. And these color signals is the combination of the different sources, like the pulse, respiration, body motion, lighting changes, sensor noise. And the idea is to demix the camera signals into two components, the PPG component and the non-PPG component. And then we can select the PPG component as the output. So a very intuitive way to do the signal demixing is to use the blind source separation, such as the well-known PCA and ICA methods. The idea is that to use the data-driven approach to estimate a projection space, either the orthogonal projection space or the independent projection space, to project the signals onto the different directions. And then on the different directions, we can select the component that is most likely to be the pulse signal as the output. And for the selection, we can use, for example, the SNR as the metric to do the selection. However, for our method, we try to use the domain knowledge of the PPG. For example, when you see these RGB signals, you will see that it has some characteristics. Like for the green channel, it has the highest pulsatile amplitude, and then the blue channel, and the channel with the minimum pulsatile amplitude is the red. And we did a large-scale study on different subjects and different lighting conditions, and make a plot the distribution of the pulsatile amplitude. And indeed, you can see that such a pattern exists in the RGB channels. The green is the most pulsatile channel, and the minimum is the red, and the blue channel is in between. And our question is that what is the principle behind why the RGB signals would show such a pattern? Our hypothesis is that it is the combination between the light penetration depth into the skin and also the hemoglobin absorption sensitivity. For example, the RGB light has different penetrations into the skin. The longer wavelength of the red can go deeper into the skin, and the shorter wavelength of the blue can only sense very shallow layers, and the green light is in between. So the order is the red, green, blue. If it senses deeper, then it will can touch more pulsatile information. However, if you look at the hemoglobin absorption spectrum, you can see that the blue is the most sensitive wavelength for the hemoglobin, and then the green and then the minimum is the red. So the order in terms of the sensitivity of hemoglobin to the light is inversed. And then a combination of these two orders will lead to a characteristic order for the camera PPG signals. Well, green is the largest, and then the blue, and then the red. So by integrating the different spectrums, like the blood absorption spectrum, skin melanin, camera filter response, and light spectrum, we can actually derive a relative amplitude of the PPG component in 3 channels, such as this factor, which we call the blood volume factor, or the blood pulse signature. And this represents the relative amplitude in 3 channels. If we know this signature, we can actually use the least square regression to do the pulse extraction, such as if we define a single signature, then we can do the single regression to extract one pulse signal. Or if we see we are not very confident about the signature, we define multiple signatures where the knowledge is more soft. Then we can get multiple regression signals, and similar to the blind spot separation, we can use the SNR to make a selection. And this is the typical use case for the single element sensing. For the single element, what we did is that we combined the full video pixels into a single pixel where the face cannot be identified or recognized. This is typically for the sleep monitoring because it's a private sensitive scenario. And then from the single element, we can use the multiple signatures to do the extraction. The reason to use multiple signatures because the skin pixels is heavily polluted by non-skin pixels during the combination. And then after using the PPG knowledge, we also think about if we can use the distortion knowledge. And actually we can, because if we consider about the skin reflections, we can consider the reflected light as the combination of the specular reflections and diffuse reflections. And specular reflections are the mirror-like reflections that does not go deep into the skin, so they do not contain any meaningful information for pulse extraction. And the diffuse reflection will include the information we want. So what we do is to design a projection space to separate these 3 physical components or optical components. The first component is, for example, the specular variation component, and then intensity variation component, and the rest is the pulse. And then we have 2 methods, chrome and pulse. The difference is in the order of doing the separation. The chrome first separate the specular and the intensity pulse, while the pulse is do the other way around. First separate intensity and specular, and then the pulse. If describing these 2 approaches in terms of the signals, and the first we project the 3-dimensional space onto a plane orthogonal to the first direction, and this direction can either be specular variation direction or the intensity variation direction. And then on the orthogonal plane, we do a second separation to further separate the one distortion source and the pulse signal. And the pulse signal will be used as the final output. And these 2 approaches only requires 3 lines of MATLAB code. So after talking about the PPG extraction, I will talk about the PPG optimization. The first optimization strategy is using the spatial redundancy. So as compared to the contact PPG sensors, the benefit of the camera is that it is an array of the pixels. It's a sensor array. If we consider each block or each pixel patch as an independent PPG sensor, we can actually do multiple extractions. The benefit is that, for example, if I'm talking and have more motions on my mouth, the signals extracted from the mouth area is polluted, while my forehead is relatively stable and the signal quality will be higher. So after separating into the spatial independent sensors, we can do a sensor pruning to get the higher quality signals. And this is the demonstration of the spatial redundancy optimization. So for example, first do the skin face tracking, the skin pixel tracking, and then we get pixel-based or block-based PPG sensor signals. And then we will do a spatial pruning, temporal filtering, and then output a clean pulse signal to separate the distortions in the spatial domain locally. However, this approach does not really work for the use case with heavy motions because that requires very accurate pixel tracking, such as optic flow. The challenge of the fitness, for example, in the fitness, the challenge will be that the motions are is much more significant and also periodic. If you see this spectrogram of the signal, this is the pulse, well, these two are the motion signals. The vertical motion, horizontal motion, are actually also periodic, and they're very difficult to be separated from the pulse. And then we propose a subband decomposition approach that extracts the pulse in the frequency domain. Because in the frequency domain and FFT domain, we can separate different frequency beams. And in the FT domain, we do the local pulse extraction per frequency band. In this way, we can suppress this periodic frequency component. Here's an example of the pulse rate measurement during the running on the treadmill. So here is the pulse rate, the continuous pulse rate. This is the pulse signal. It's showing in real time. And if I increase my running speed, you can see my heart rate is going up. And here's the camera. And the third approach of optimization is using the discriminative signatures. It solves the challenge of the PPG extraction in the near infrared. Because in the near infrared, the challenge is that as compared to the RGB, is that the PPG has much lower amplitude and also much lower contrast. So it's much more difficult to be differentiated from the motion distortions. And here what we propose to use the pulse extraction combining with the motion traces. For example, if I use the facial landmark tracking, I can get three-dimensional color signals and 2 additional motion signals. And then I will use the 5-dimensional signals for joint extraction. And similarly, I use the discriminative signature to specify my expectation, and I set these 2 entries as the 0, and then do a least square regression to suppress the motion signals in the motion components in input signal, because here my expectation on the motion components is set to the 0. And this way, we can somehow robust to the distortions, motion distortions in the near infrared. Yeah, here is the PPG signature based approach, and you can see the pulse rate is like this. And by using the motion signals as the additional input channel, we can reduce this errors measurement. Then recently we also see that there's a trend of using the CNN to measure the vital signs from the video in an end-to-end fashion. So the core idea is that of the CNN is to learn the extraction from the data such, for example, to map the video extraction to a contact sensor. And then we did a study, try to reproduce the CNN-based approach and also to understand the limitations and sensitivities as compared to our conventional approach. And here I would summarize our main findings or conclusions. But first is that we find that the CNN indeed measures the PPG. It's not only the BCG or ballistic cardiographic motion, because if we used RGB camera to train the CNN, and if we reverse the order of the RGB channels, for example, test on the BGR order, it will not work. That means the CNN really learns about the blood absorption variation because that's wavelength dependent, not only the BCG motion, but we cannot guarantee that it does not measure the BCG. And actually, this is quite critical for medical applications if it measures the both. For example, it cannot be used for the SpO2 measurement. And the second is that if we want to train the CNN, that the physiological delay between the contact reference, like the finger PPG or the ECG and the camera, must be considered. Because there's a physiological delay, that means the signal, the camera signal and the labels are not synchronized. And we show that in the paper that this is quite critical. And the third is that by using the normalized frame difference as the input, the spatial convolution of the CNN seems not very critical. For example, if we train the CNN with the frontal face and test with the side view face and the rotated face, it still works. But that means the spatial convolution is not really important. And the fourth is that we find the combination with the physiological model-based approach, our method, Phosphor LED, still improves the result. For example, if the input of the data has been pre-processed by Phosphor LED, and then that improves the measurement. And finally is that the proper benchmark is needed because we find most CNN works that do not properly benchmark against the conventional approach. A proper benchmark should be CNN versus spatial redundancy and the PPG extraction because the CNN already used the spatial redundancy. Now we come to the camera PPG hardware part. So we have two solutions. The first is the visible light solution. The second is the invisible light solution in the near infrared. For visible light solution, we use the regular RGB camera and ambient light as the light source. And for the near solution, we require a near infrared camera, and it is preferred to be the multi-wavelength because we showed that by using the multi-wavelength, we can gain a much more robust extraction performance. But then we require the camera and also the active near infrared light source to be multi-wavelength. And at the moment, there's no multi-wavelength near infrared solution available, so we need to construct our own setup. And here we propose two camera setups. First camera setup is the multi-camera system, which we use multiple monochrome cameras, and each monochrome camera has its own near infrared cut band. For example, the 760 nanometer, 800 nanometer, and the 905 nanometer, centered at 3 different wavelengths. And here, but there's one problem for this system is that there are parallax between the cameras. That means that if the two cameras that they are seeing the object or the face at different distance, this parallax effect will be different, and that will cause the color gradients. As you can see that in the image, although we can use the camera registration or image registration to align the image planes of the 3 cameras. But if you zoom into those details, you can still see these color gradients. Because when doing the extraction of the PPG or the other pulsatile information, like the blood oxygen saturation, we rely on the colors. So any small color gradients or shift will be a big problem. And then it comes to the second solution, which we use which we call the RGB to near. We adapt an RGB camera to a near infrared sensor, and it is also multi-wavelength. For example, for all the RGB cameras, although it sends the RGB part, it actually has the infrared band leakage. And then now we did a modification to the RGB camera by remove the RGB by removing the IR block filter and then add a dual band IR cut filter. In this way, we change the sensing part from the RGB to the near infrared, and it is a dual band. And the image, the DC image, has been changed from RGB, you can see, to the dual band IR. But then now you may have a question why we use the dual band filter here. Why not just use a broadband RGB filter here to sense the whole part? The reason is that we found the dual band can actually improve the extraction performance. And here is an example that if I put the full band near, you can see this is DC image, and this is the measured 3 wavelength signals, and this is the relative contrast between the PPG amplitude in these 3 channels. And this is clearly smaller than the contrast between the dual band near infrared. If the contrast is larger, it is easier to differentiate from the motion distortions. And also you can see the difference in the image DC. And after talking about the camera solutions, we also need active near-infrared light source, and these also need to be multi-wavelength. For the near light source, we have 3 different options: the incandescent light, which we used in the experiments, but it's not practical for a real use case. And the second approach is single wavelength narrowband infrared LED, which is the typical solution for current IP cameras or night vision cameras used in CCTV. But this is not suitable for our approach because we need a multi-wavelength infrared light source. So an intuitive solution is to integrate multiple LEDs with the different wavelength on a single board. And we did that, but we found there's a problem. It's the color inhomogeneity. That because this board have a different LEDs, and the LED has different wavelength. So if there's a subject sitting or standing in front of this light source will emphasize different part on the face or in the space. So if you have some small motions in front of the light source, then it will pollute the measurement. For example, I put an example here that 3 subjects, 3 with different skin types. If there's no motion, then we can somehow measure the PPG frequency component. But if there's some small motions, and this motion will change these color characteristics because the color is not homogeneous here, then it will bring some problem. And then to solve this issue, we propose our own light source, which is based on the phosphor LED. So the idea is that we use the blue LED to emit the blue light to the phosphor material, and this phosphor material will emit broadband light, and then by adding a IR block filter, we can remove the visible part and keep the continuous spectrum part of the near-infrared. And this is the optical response of the phosphor LED. So by adding a band cutting filter, we can emphasize this part, and this band, the spectrum band of this phosphor LED is continuous, and it satisfies our requirements for the multi-wavelength sensing. This is how it looks like. It's a home-built light source. Then this is just one example of the measurement, but more statistical measurement has been reported in the paper we published this year. Now we come to the second part, camera-based respiration monitoring. First, I will introduce the motion-based respiration measurement that use the motion tracking or motion analysis to capture the exhaling and inhaling motions. The first method is the pixel flow decomposition. For example, by using the optic flow, we can capture the pixel movement, and then we store the pixel movement into traces and decompose the trace and select the component that is related to the respiration signal as the final output. The second approach is the profile correlation, which is the main invention of our group. The idea is also quite simple. It's select the region of interest as for example, the chest, and then derive the profile for each chest. It can be a vertical projection of the pixels, and then we estimate the profile correlations in the time, and from the correlations we derive the respiratory signal. And here's an example of the motion-based respiration. And these are the measurement of the babies in the home-based monitoring and also in the neonatal care unit. And here is an example on the adult subjects. And here we used automatic respiratory ROI detection. For example, we cut the full video into different blocks. And for each block, we estimate the respiratory motion and select the ROIs that contain the strongest signal. Later we find that the respiratory motion, or say the respiratory signal direction, is related to the posture of the subjects. That means we can use this measurement to estimate the subject pose. So by giving an input video, we first do over segmentation, cut the video into the different blocks, and for each block we estimate the respiratory signal on the X directions and also on the Y directions, on two orthogonal directions. And based on the two orthogonal signals, we estimate their angle. And from the angle, we can detect the pose. So this is based on the physiological measurement and the modeling. It does not really need to see the body skeleton or the torso of the subject. Even the subject has been covered by a blanket. As far as you can see the respiratory motion, you can measure its posture. And it does not require the data training. It has been filed as a patent. And here is an example how it works. The blue means the negative angle, respiratory angle, and the red means the positive angle. So if the subject is turning the directions or turning around, you can see that the distribution of the angle changes. And from the distribution of this angle, we can derive the sleeping posture. And for the sitting position, for the sleeping position, sleep with the blanket, and also the different viewing angles. And the second approach to measure respiration is thermal-based. The idea is to measure the airflow induced temperature variations in the nostril area. For example, you can already see from this thermal image that the intensity is changing due to the respiration. But this is quite sensitive to the different view angles. If you cannot see the nostril ROI, you cannot really measure that. And this is some results that we can measure the respiration from the thermal camera in these two views. For example, the bottom view, it shows clear signal, and for the side view with the pillow, it also shows signal. It's quite interesting because actually the ROI is not on the nostril, it's on the pillow, because you change the temperature of the pillow. And for the other three views, the signal is not really good. But we can still use that. For the current coronavirus case, the reason is that in many countries, everyone need to, or most people need to wear the facial mask. And then the facial mask can clearly increase the measurement ROI, because when you are breathing, then you change the temperature of the whole mask. Here is an example of this measurement. You can clearly see that the mask temperature has been changed. And by just extract the temperature changes without any post-process, you can already see a clear respiratory signal. And this is different from the motion-based measurement because motion is still kind of the surrogate of the respiration. But this one is really due to the airflow. And this method can be used for the hospitals or the clinics, especially in the RFID case, for the general ward, for the emergency department triage, for ICU monitoring, or kiosk screening and gating. And we also proposed a solution for this measurement by using the cheap thermopile, which is a low resolution thermal array sensor. It has only 8 by 8 pixels and the temperature range and the temperature accuracy is not very high. But the good point is that the price is very cheap. The reason why we can use the thermopile solution is that because the facial mask it already increased the ROI size, so we do not really need a high resolution thermal camera. And here's an example in our paper that without the facial mask we need to measure the nostril ROI, then it's very sensitive to the distance. Only when we put the thermopile like 5 centimeters distance to the nose, then you can measure the breathing signal. If it's 10 centimeters, it already does not show a good signal. But with the facial mask, if you wear a facial mask here, you increase the ROI, and then even at the distance of 50 centimeters, you can measure the respiratory signal. And these signals are raw signals without dedicated processing. And this approach can be integrated into current gating systems that to do fast screening or checking. And then the other measurement, what we think about is the nose breathing or mouth breathing classification, because we need to prevent the habit of mouth breathing. And there are actually already some products preventing it, but clearly there's no approach to measure the mouth breathing. And the mouth breathing has many drawbacks or harm our health. For example, the chronic allergies, the hay fever, asthma, the chronic stress and anxiety. But by using the thermal camera based approach, we can easily differentiate the nose breathing and the mouth breathing. And we also want to stress that this is the first kind of this measurement. That's not even the contact sensor can measure the nose breathing or mouth breathing. And here we mentioned that we are not interested in the respiratory signal. We are more interested in which ROI has been used to breathe. For example, it's also quite a simple approach that we detect the ROIs, the nose and the mouth by using the facial landmark. Then we can crop these two areas, and then we just use the hawk features to extract the descriptor from this area, and then we can tune a binary classifier to differentiate these two classes and detect mouth breathing or nose breathing. And then if we measure the subject over the night, we can give a percentage like the mouth breathing, and use that as an early indicator for the subject to improve this habit. And here is an example of our study, the result of the study. That experimental protocol is following this. First, we use the nose to breathe, and then the mouth breathing, nose breathing, the mouth breathing. And we test on 8 subjects, and you can see that this is the mouth breathing, the energy that we measured. Now we come to the part 3 applications. I will mainly introduce 2 applications. The first is the VitalSign app, and the second is the VitalEye. The VitalSign app, this is the app that co-developed between the WinSocial insurance company and the Philips Research, where they used our VitalSign measurement techniques as their built-in function to measure the subject heart rate and respiration rate as a kind of the pre-screening. If you're interested, you can download at the Google Store and play around. The second is the VitalEye product that we integrate the camera-based respiration monitoring on the MR machine to improve the scanning. So the challenge for the MR imaging is the respiratory motion, one of the challenges. because the respiratory motion can lead to the motion artifacts in the MRI imaging. And there are two possible ways to avoid these artifacts. The first is the breath holding, to ask the patients to hold their breath during the period of the scanning, but this is not preferred. And second is the respiratory triggering, that try to synchronize the scanning of the MR machine with the respiratory movements. And the synchronization can be done by the contact sensors, for example, the respiratory belt. This has already been used in practice, that the users will, or the patient will wear this respiratory belt, and then to sense the body movements, and use the body movements, the respiratory signal, to synchronize the scanning of the MR machine. And the other approach is to use the VitalEye, that we have, for example, the camera here to sense the respiratory motion, and here is the active infrared light providing the illumination. And by using this, the whole process can be fully automatic and does not rely on operators. It's always on, also improve the MR imaging quality, and it can give the immediate feedback of the breathing signal to the operator. And here is an introduction how it works. Yeah, so here is the front of screen that the caregivers or the clinicians can see the respiratory signal. Previous setting, they used the respiratory belt. Now they don't need to use that. And here is the VitalEye setting. This is the VitalEye, the camera, and this is the ball light, providing the illumination. And the respiration signal is captured in real time. An MR machine is synchronized with that. And here is a basic illustration of how it works. So this is the view of the VitalEye. It will do the automatic scanning of the patches and find the ROIs that contain the respiratory energy. So it does not require the operator to define the ROI. And this is how it looks like inside. The VitalEye has this angle, and it extracts the respiratory signal from the chest area, for example, and detect the peaks and use the peak to trigger the MR scanning. Now here is an example of the imaging quality of using the VitalEye. This is obtained by using the respiratory belt, and this is by the camera. And you can see the comparison that the motion artifacts or motion blurs has been reduced by using the camera. So in the end, I would also like to introduce you our special issue on IEEE-JBHI. Currently, we are organizing a special issue of the camera-based monitoring for pervasive healthcare informatics, and we welcome you to submit a journal paper to our special issue, and the deadline has been extended to August 1st of this year, and we look forward to your submission. Thank you. If you have any questions, I'm glad to answer, and otherwise you can send the questions to my email.